Good morning, everyone. My name is Renxuan Xie, a postdoc from UC Santa Barbara. I would like to first thank the organizers and the session chairs for this opportunity to share my most recent work. Today, my talk is focused on developing new, super soft, solvent-free elastomers that are compatible with more advanced processing methods needed in practical applications. At this AICHE annual meeting, I prepared two talks. One is on photo-crosslinking, the other is on 3D printing. For this presentation, as the title suggested, it will focus on the universal methods to photo-crosslink Bottlebrush polymers. Bottlebrush polymer is known to form super soft, solvent-free elastomer. But what is a Bottlebrush polymer? Let's first start with the linear polymer network that we're all familiar with. In this case, each polymer is linked together by red crosslink points. Also, entanglements, represented by the green points, act as additional physical crosslinks. On the other hand, Bottlebrush polymer, which has a backbone attached with unentangled side chains, they don't show any entanglements between crosslink points. Because of this property, Shekel and co-workers were able to mimic biological materials such as jellyfish by engineering the Bottlebrush architectures. Our previous work has also exploited this property for a capacitive pressure sensor. Because of the super low moduli, we're able to increase the sensitivity of the sensor by 53 times comparing with the linear analog. But how to make the Bottlebrush network? Current approaches involve processing by simple and slow molding that dramatically limits their utility. As shown, a mixture of macromonomer, macro-crosslinker, and solvent is sandwiched between two plates and slowly reacted to form the swollen Bottlebrush network by heat or UV exposure. So post-curing steps such as deswelling and drying are also required to form the dry network. Also, because the elastomer is formed directly from monomers, there's no direct comparison between the polymer and the final network. Therefore, the objective of our work is to first develop a new cross-linking process that is fast and solvent-free, and then use this approach as a stepping stone to achieve 3D printing. The 3D printing part is presented elsewhere in another talk on the AICHE virtual platform. So for the remainder of the presentation, let's first focus on developing the new photo-crosslinking process. Our approach starts with a mixture of Bottlebrush polymer and photo-crosslinker, which will have different sidechain chemistry and different linker chemistry. And by matching their chemistry and similarity, we can assure good miscibility between the two components. And then by shining the UV light, the polymer can be directly cross-linked to form the Bottlebrush network in a solvent-free state. Our design approach is potentially advantageous because of the solubility in a wide variety of Bottlebrush matrix without solvent. We also expect that a much faster cross-linking reaction from the Bottlebrush polymer rather than from a mixture of macromonomer and crosslinker. In order to demonstrate the excellent solubility of photo-crosslinkers in different Bottlebrush polymers, we have conducted the differential scanning calorimetry test that tracks the glass transition temperature of the mixture as a function of photo-crosslink loading. For example, here on the slide, we tested the solubility of EMH BSPP photo-crosslinker in a Bottlebrush polymer with either polybutyl acrylate as a sidechain, or in another Bottlebrush polymer with a poly,4-methyl caprolactone as a sidechain. As you can see on the plot on the left, as long as the weight percent of photo-crosslinker stays below 30 weight percent, it is clear that only a single glass transition temperature is observed, and it shifts to a higher temperature as more crosslinker is added. Then we can confirm the amount of the shift in TG actually follows the expected Fox equation very well for both mixtures. And also I will point out that only 2 weight percent of crosslink loading or less is actually sufficient to form a robust and super soft network in the actual UV curing test that I will show you next. Indeed, let's first take a look at a particular Bottlebrush polymer with a butyl acrylate as a sidechain and at a specific crosslink loading NCl equals to 11. As shown, the UV light exposure resulted in an immediate rise of the storage moduli and loss moduli. After about 200 seconds, G', J' crossover, which represents the viscoelastic liquid to solid transition. As curing continues, G', J' eventually plateau, indicating the completion of crosslinking. Then, by adjusting the crosslink loading, we can change the storage modulus by roughly an order of magnitude. We can again apply the same method to other pairs of crosslinker Bottlebrush polymer with different sidechain chemistry. The equilibrium network moduli, G of x, is defined in the low frequency limit, and in this case, 10 to the minus 3 radian per second. However, additional network modeling is needed to not only control, but to predict the moduli from the Bottlebrush network structure. Here, let me first briefly summarize the previous approaches in the literature. One approach assumes that all crosslinks are elastically effective, meaning that all crosslinks are stress-bearing and linking the nearby polymers together. This assumption essentially treats the elastically ineffective crosslinks as the only two dangling ends per chain. In the other case, the crosslink chemistry is designed in a way such that the crosslinks are only allowed on the backbone of a Bottlebrush polymer. And because the chance of looping for both crosslinker and Bottlebrush polymer is really rare, this scenario essentially also assumes all crosslinks are elastically effective. But the main concern of applying the previous approaches in our system is the indiscriminate nature of the benzophenol-mediated crosslinking, meaning that the benzophenol unit can link with any nearby hydrocarbon unit upon UV irradiation. So there will be a number of crosslinkers that we added are not elastically effective and are actually embedded inside the brush region. So the total crosslinkers that we added are therefore a sum of elastically effective and ineffective crosslinkers. So how do we relate G of x, which is an equilibrium network modulus, to the crosslink loading and the total number of elastically ineffective crosslinks? To address this issue, we decided to build our own model by making the two main assumptions below. First, because the crosslink functionality is uncertain, so that we introduced the proportionality constant A to relate the network moduli to the number of elastically effective crosslinker between the two ideal limits, namely the affine network and the phantom network limits. Secondly, we assume that the elastically ineffective crosslinkers is actually proportional to the molar mass Bottlebrush polymer. The proportionality constant B represents the number of intro-Bottlebrush crosslinkers per unit molar mass of a Bottlebrush polymer. And this value B should only depend on the specific combination of polymer and crosslinker. Given the same total number of added crosslinkers per unit volume, the smaller the molar mass of Bottlebrush polymer should lead to a greater probability of inter-Bottlebrush elastically effective crosslinks. After some calculation, we can simplify the relationship between the network moduli and the added crosslink loading with two fitting parameters A and B. To validate the proposed model, we have determined the network moduli for a range of different Bottlebrush polymers and crosslink loading. The dashed line is a phantom network model, assuming all crosslinks are elastic effective. The solid line is the best fit of the data using our proposed model. The fitted parameter is summarized below. And we can apply the same study to the other systems with different sidechain chemistry, and all of the fitted parameters do fall within the expected limits. The main power of this model is to predict the softest moduli possible for a given Bottlebrush polymer. And indeed, we have achieved super soft moduli around 10 kilopascal without sacrificing the gel content. And we can repeat this process for other Bottlebrush polymer with different side chain chemistry as well. In summary, we have presented a fast, simple, and versatile approach to form Bottlebrush network, which can be well described by our general model between modulus and crosslink loading. This model provides a clear way to differentiate and quantify the number of elastically effective and ineffective crosslinkers in a Bottlebrush polymer matrix. By relying on this model, we can accurately control and predict the network characteristics of a super soft, solvent-free elastomers with high gel content. Finally, I would like to acknowledge Dr. Sandra Mukherjee for synthesizing the Bottlebrush polymers and photo-crosslinker mentioned in this talk. And would also like to thank Veronica Reynolds for helping me with the 3D printer. And of course, I would like to sincerely thank my both advisors, Professor Michael Chapnick and Professor Chris Bates, and both group members. I would like to also to acknowledge our funding source, Mitsubishi Chemical Center for Advanced Materials at UCSB. And I would like to finally thank you for your attention and looking forward to the live Q&A session. Thank you.